Welcome to Free Calculus Honors, eh?
I miss you, Danny. Come back, please.
Love
You
you,
too,
Josh.
Josh, but mostly Danny, please.
Josh, we miss you. I'm going to talk to you from the meta future again, but from the past also.
All right. So, your entire life you've been graphing. Well, the second part of your entire life you've been graphing. And you've been graphing in what we call rectangular coordinate systems, or the Cartesian coordinate system, where basically your axes are, two perpendicular lines, a straight horizontal line and a straight vertical line, which together makes a rectangle. That's what you've been graphing on, right? And so if you have a coordinate, then, if you have a coordinate x, y, how do you get to that coordinate point? Well, you go, x units to the left or right, and then you go y units up or down, and that's how you get to your coordinate, okay? However, it turns out not everything in the universe is rectangular. In fact, the very planet that we live on is not a rectangular solid, right? It's a sphere. So, well, sort of a sphere. So, it makes sense then to have another coordinate system where it's not, straight horizontal and vertical lines, where we account for this circular world that we live in. And for that, we have the polar coordinate system. So the polar coordinate system is, we're going to talk about the two-dimensional system, in which each point is not just defined by, okay, go to the left and now go up. No, each point now is defined by a distance from a fixed point and an angle from a fixed direction. Okay? What does that mean? That means if you're at this point here, to go to your coordinate, you go across a little bit, and then you go up or down a specific angle, and that's how you get to your coordinate. Okay? So, in the polar coordinate system, let's talk about this for a minute. The origin, what we used to call the origin in the Cartesian, is now the pole. Okay? So not the origin, but the pole. The polar axis is a ray that extends from the pole. Okay? And polar coordinates are defined by r and theta. So now in this new world, we no longer have x and y. That's a thing of the past. Now it's r and theta. Okay, so why do we need two variables? Because we have two dimensions. We have a distance and we have an angle. We have an r and we have a theta. So suppose you want to give somebody an address, where to go. Well, you give them two coordinates, r and theta, 2, 30 degrees. What does that mean? You start from the pole, you go over 2, and then you go up 30 degrees, and you get to that point. Do you see that? And with this, think about it. You could redefine every single coordinate in space with this. You just go over a little bit, and then you span a certain angle, and you can get to your point. Okay? So rather than walking in a rectangular pattern, you go across, and then you span a certain angle. It's going to require none of it, because we have a different grid with all of the angles defined for you. It's so awesome. Oh my God, like so much awaits you. Okay, so what is r? In the rectangular coordinate system, when you have x and y, they're each, it's so boring, like they're each like just the distance from the origin, either left or right, horizontally or vertically. Well, now r is directed, it's the directed distance from the pole, and theta is the directed angle from the polar axis OP. So you've got that polar axis here, it's the angle from it, just like when you were drawing angles from the standard position. Okay, so how do we graph a point in polar coordinates? If you have a positive value of theta, that just means you go counterclockwise from the polar axis, just like when you were drawing in chapter 4, an angle from the standard position. Okay, so positive is always counterclockwise. Now, what about r? That takes care of theta. What about r? If r is positive, then P is on the terminal side. So you draw the angle, and on the terminal side you have your P. But if R is negative, then you have to go from the terminal side, you have to go on the opposite ray. Okay? So what do I mean by that? Here's your pole, and this is the polar axis, right? This is where we would start drawing angles before in standard position. So suppose you want to go up 30 degrees. You go up 30 degrees. Now this is your terminal side, right? Okay, so suppose you go over 1, 2, 3 spaces right there. So now your R is 3 and your theta is 30. So this is the point 3, 30. Do you see what I mean? Now, what if you wanted to do 30 degrees but a distance of -3? Well, if you wanted to do that, here's how that would look. You would go 30 degrees, and if you wanted to go -3, then you don't go on this axis, on this line, you go on the opposite ray. So this way, 1, 2, 3 units that way, and that is -3 and 30. You do the angle first, and if it was positive, it would be on the terminal side, but if R is negative, then you go on the opposite ray. Okay? Do you remember what opposite rays were? You have, this is a ray, and guess what? If you go in the opposite direction, then you've got an opposite ray. Okay, so these are opposite rays. All right, so let's graph these now. It says to graph each point, so you have S at 1, 200 degrees. So here's your pole. All right, here's your horizontal. Now, if you're going to go 200 degrees, where is that? Here, right? And where would your, what's your R here? 1. So how much would, what's the distance that you go? 1. So here, okay, so that's the terminal side, right? Now you go a distance of 1, so that's your P, that's your S. Well, we're just graphing randomly here. Eventually we're going to graph on an actual grid. Okay? All right, so here's another one. We're going to go -2, a distance, an angle of 3 pi over 2. So here's your pole. That's the polar axis. If I go 3 pi over 2, that's this, right? 3 pi over 2. Now, it's -2. -2 means you're not on the terminal side. You're on the opposite ray of the terminal side. So you go a distance of 2 on the opposite ray. You don't have to, no. Okay, so that's where your R is. Oh no, it stopped recording. Oh no, it didn't. Okay.
We're almost gone, but we're still back.
All right, so just as rectangular coordinates are graphed on a rectangular grid, polar coordinates are graphed on a circular or a polar grid. So this is a polar grid, right? And if you notice, okay, so here, this is the pole right there. So if you notice, if you go radially away from the pole, okay, each one of these lines that you hit, that's 1 unit. So suppose like you're here, this is 1 centimeter, 2 centimeters, 3, 4. Now if you go in this direction, it's 1, 2, 3, 4. Okay? Again, this is the polar axis. If you go counterclockwise now, you process through the angles. So you have pi over 6, pi over 3, pi over 2, and so on and so forth. Okay? Now, let's graph 4 pi over 3, a distance of 3. Okay? So we have a distance of 3 at 4 pi over 3. So where is 4 pi over 3? That's right there. Right? We go that way to 4 pi over 3. Now, we're at a distance of 3. 1, 2, 3, right there. That is your P. All right? Just the point is fine. Here we have an angle of negative 240 degrees. That means we're going to go this way. From here, we're going to go to negative 240, which is where? It's right there. Now, my terminal side would be here. But because it's a negative 2, now I have to go in the opposite direction. 1, 2, right there. Okay? Is this making sense? So there's a typo here. This should say infinitely. So recall that an angle has infinitely many coterminal angles, right? So if I draw an angle of 40 degrees, and if I go 360 more, so at 400, it's the same angle, and then at 760, it's the same angle, and I can keep going 360, and I'm going to get to the same angle. Well, since that's what we're doing here, right, I could have gone 4 pi over 3, and then another 2 pi, and then another 2 pi, and then another 2 pi. I would still get to the same point as long as the radius is the same. Yes? So in polar coordinates, that holds. So if a point has coordinates r theta, then you could keep adding 360 to the theta and you just get the same point. Or you could keep adding or subtracting 2 pi and you get the same point. Now, similarly, what if you have a point right there? Okay? You have a point right there. And suppose that's a distance of 2 units. Okay? Now, if you go 180 degrees away from that, where would that take you? Right there. Okay? But instead of 2, if I had negative 2, then I get back to the same angle. Okay? Does that make sense? So we're gonna try this for a little bit. So you can also change, if you had r theta, you could add or subtract 180, but make this negative and you get to the same point. So you could add or subtract pi, but make r negative and you get to the same point. Well, let's try that. It's not very intuitive.
But when you do that, you can't also have an infinite number of those. You can only have once.
But you can keep adding 180s and you can keep switching the signs.
Oh,
if you add 2, yeah, you do it twice. Okay. I mean, you do them together. Okay, so look, here we have 70 degrees, which is going to be right about there, and a distance of 2. So 1, 2. That's where my angle is, right? I mean, that's where my point P is. Okay? Now let's graph a r of 2, but an angle of 430. Well, where is 430? Here I'm at 2. 1, 2. Well, okay, so 360 plus another 70. That's where my P is now. Look, it's the same point because I added 360, right? So what is this? This is just 70 plus 360. Well, what about this one? Let's go to a distance of 2. 1, 2. Now let's go a distance of negative 290. Boom, right there. P. It's the same point because this is 70 minus 360. So you can add or subtract 360, you get to the same point. Now let's try this one. I have a distance of 3 and 50 degrees. So let's do this. 1, 2, 3. Now I'm going to go up 50 degrees. That gets me to here. Okay? Now I'm going to graph the other one. Well, what's changed here? I have a negative, and this is 50 plus 180. So look at what's going to happen. I'm going to graph 230. So let's go to 230. That is, where is that? Right there. Right? 230 is right there on that line. But my R is -3. That means I have to go on the opposite ray. Okay, 1, 2, 3. Same exact point. Okay? One more time. -3 and -130. So what happened here? I changed this to a negative, and this is 50 minus 180. So let's go to -130. Where is that? Right there. Yes? Is it right there?
Yeah, it's 230.
And then I go up here. Wait a minute. So 90 here. Okay? So now I have to go -3 though. So rather than it being on this line, it's on the opposite ray, 1, 2, 3, right there. Okay? So just a little illustration. Okay. So with the same process, we can now be given a point. In this case, we're given this point. And we have to find 4 different pairs of polar coordinates that name this point. Okay? And we want S to be between -360. We want theta to be between negative and positive 360. All right. So what is that point? Where is that point? First of all, it's at 210, and what is R? It looks like it's 2. Okay? Right. So what's another one? What's another thing we can do? So the 2 things we can do is we can either do R comma theta plus or minus 360, or we can do -R comma theta plus or minus 180. Now, can I do 210 plus 360? Is that within my domain? No. Can I do 210 minus 360? I can do that, right? So I can do 2 comma 210 minus 360. How much is that? -150. So that's my second one. So here's 1, 2. Now what else can I do? I can do -2 comma what? 30, because it's 210 minus 180. What else can I do? Can I do 210 plus 180?
Yeah,
Negative.
no, minus 180. Because then, or plus any.
What else can I do?
210 minus 360.
210 minus 360, I already did that.
I mean, like, but you do the negative side, so it's going to be -330. And then you do the opposite of -330. Like, so it's going to be -2 comma -30. No, -2 comma. And we're back.
So another thing you can do is from here, you can subtract 360. So it's -2, 30 minus 360, -2 comma -330. So that's the 4th one. All right? Okay. So polar equations. A polar equation is an equation expressed in terms of polar coordinates. So for example, r equals 2 sine theta, okay? That's a polar equation. All right, so let's graph this one. Remember, we want a graph that satisfies a given polar equation. So here I want to graph r equals 2.5. So right now, we're just graphing the very, very basic case. So suppose this was in rectangular coordinates, x equal to 2.5, y equal to 5/2, and so on, right? So that's what we're doing. So we want r equals 2.5. So for any angle, let's just pick r equals 2.5. Where would that be? R equals 2.5. Okay, so if this is 1, 2.5. If my angle was 0, then that's 2.5. Well, somebody could say, well, wait, what if your angle was 90? Where would you be then? 1, 2, 2.5. Well, what if your angle was 180? Where would you be then? 1, 2, 2.5. What if it was 3π/2? 1, 2, 2.5. So basically, what am I doing here? I'm graphing the set of all points that satisfies this condition. What's that condition? That you're radially 2.5 away from the pole. Okay? It's exactly a circle. So you learn, that's one of the first things you learn in geometry. What's the set of all points? That's like 5 centimeters away from a point. So if everybody, it's a circle. If everybody was supposed to stand 3 feet away from me, if I told you, get up and everybody stand 3 feet away from me, you would all be in a circle around me, right? So this is the set of all points that is radially 2.5 units away from the pole, okay? So radially 2.5 units from the pole. So that gets you a cute little circle. Okay? No, it's not. It's tough on the it's tough on the screen. You need classroom experience for that. All right. So theta. Okay. So now I want the set of all points. That's 5π/6. That has an angle of 5π/6 from the polar axis. All right, so here I am. If my radius was 1 and I went up 5π/6, that's where I would be, here. If my radius was 2 and I went up 5π/6, I'd be right there. If my radius was 3 and I went up 5π/6, I'd be right there. Well, if my radius was -1 and I went 5π/6, 5π/6, but -1, I'd be right there. What is that looking like?
Straight line.
That is a straight line through the angle 5π/6. Okay? I'm taking a lot of time with this now, but really I'm just, laying the groundwork because I realize none of you have seen this before, but this stuff should really take you like seconds, fractions of a second to do. Okay? Yeah. Just wait. So, okay. Distance. Because you've got two planes. By the way, these polar coordinates are used when, pilots are flying to give them direction, to give them, whatever, coordinates and so on and so forth. So now you've got two planes in the sky, and you have to calculate how far apart they are from each other. Well, you can't use the distance formula for the rectangular coordinates because they're not on a rectangular coordinate system. They're on a curved surface in the atmosphere. Okay? So you have to account for that. So look at this. We know the distance formula in the rectangular system, right? It's the square root of x2 minus x1 squared plus y2 minus y1 squared. That's it, right? Well, what is this really? It's the distance between the two in the x coordinate. It's the distance between the two in the y coordinate. Well, there is none of that now. Now everything is just in relation to the pole, in relation to the origin. So I got one plane here, one plane here. Everything is in relation to the origin. This is the distance of plane 2 from the origin. This is the distance of plane 1 from the origin. So I got R1, I got R2. Okay, come on. We just did vectors. Okay, we know about how to find the angle between two vectors. It's all about that cosine, right? R1, R2 cosine, remember that? Okay, like in Math Nirvana, all of this is related, all right? So that's where this comes from. I'm not going to do the derivation of it today. I might do it at some later point, but I'm not going to do it today. It's the difference of the angles from the origin. Huh? That's exactly what it is. That's exactly what it is. See?
Jacob was right all along.
It's all related. Okay? So you want the theta in between here, yes? You want the theta, that red angle. Well, how much is that red angle? It's that entire angle from R1, from the origin to R1, minus the entire angle from the origin to R2. Now, does it matter if you do cosine of theta 2 minus theta 1, or if you did cosine of theta 1 minus theta 2? Does it matter?
Yeah.
Does it matter?
No.
Well, it's either a yes or a no.
No.
Well, you can't just say yes or no because you're 50% right. Justify your answers. Don't plug it on the calculator. Justify it mathematically. Come on, Jacob. You can do this.
Okay, pass. So,
What's the function here?
so 0 minus 360.
What's the function? Cosine. What type of function is the cosine? Ooh. Is it an odd function or an even function?
Even function, so it doesn't matter.
It's an even function. So cosine of theta is the same as cosine of negative theta. Now, if that was a sign in there, it would definitely matter. Okay? All right. Yes. Okay.
Thank you. That was the first time anyone's ever complimented me on a pod.
I still miss you, Danny. Come back.
All right. An air traffic controller is tracking two airplanes flying at the same altitude. So that's important because if they're flying at the same altitude, they could potentially crash. Okay? The coordinates of the plane, which goes to show you that you could do all of this in 3 dimensions as well, right? So where they are here, and then, give it some height. That's when things get really interesting. Oh my goodness. Then there's a phi in there. Oy. Okay. So, an air traffic controller is tracking two airplanes. The coordinates of plane A are this, and plane B are this. So first it just says to draw the graph of the situation. All right, so where is plane A? So now we're going by 4s and 8s. So what I'm going to do is calibrate this so that it goes up by 2s. So this one is 60 degrees and radius of 8. So we're at 60 degrees here. 2, 4, 6, 8. There is plane 1. Okay? Now where is plane 2? It's a unit of 4, but at 3, it's a distance of 4, but at 300. So right there. P2. So here we've got, that's R1. And this is R2. Okay. How far apart are the two planes? When it says how far apart are the planes, the distance that I want is this one. Oh, look, my R1 disappeared. Almost. Yeah. Okay, so we're going to plug it into the formula. And the formula says that the distance is the square root of r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2 minus theta 1. Okay? So now, this is a distance of, what is my r1 and r2? 8 squared plus 4 squared minus 2 times 8 times 4 times cosine, or 60 minus 300. It's the cosine, we don't care. Just calculator from here. So, I don't know why this is highlighted. Well,
I got you. About 10.58.
Yeah, I got 10.58.
okay, that's the full distance. So it's 10.6 miles. Boy, they are.
Yeah, they're fine.
Well, it depends on what direction they're flying.
Yeah, it's flying the same.
We don't know. We don't know the direction that they're flying. If they were flying towards each other, we have like 10 miles. That's like 2 seconds. Okay? All right.
Yeah, 600 miles an hour. It's not great.
Yeah.
Like they're racing each other. First one in New York wins. Speaking of, can I show you a video of how to
All right. So now, this homework. Whoops. Will be due Thursday? Thursday. Okay. And